Welcome to ECECS 552, lecture on instruction sets with a focus on the x86 instruction set. To recap briefly, in the previous lecture we covered the MIPS instruction set, which is the one we'll be using in 552. However, the most common instruction sets in use today are the x86 instruction set by Intel and the ARM instruction set. x86 is primarily used in desktop computers and laptops, and the ARM instruction set is used in smartphones and other embedded systems. In this lecture, we want to look at an example of a more complex instruction set in contrast to the very simple and regular instruction set that we looked at in the previous lecture, which is MIPS, and that instruction set is x86. Before digging into the details of x86, let's talk briefly about some of the trade-offs that come into play when we're designing an instruction set. One of the main trade-offs that people considered very, very important 20 or 30 years ago was what's called the semantic gap that exists between a high-level language and the low-level machine primitives that actually then implement the semantics of the programs written in that high-level language. This semantic gap was used to motivate complex features and complex instructions in an instruction set. A couple of examples of this would be, first of all, providing direct support for function calls, which were viewed as something that would be difficult to implement with simple primitives. So instead, many of the older instruction sets would include instructions that would do all of the work required to implement a function call, namely allocate a stack frame off the stack, push parameters onto that stack, push the return address onto that stack, push the stack pointer itself onto that stack, and then finally transfer control to the subroutine or function that was being invoked. And then, of course, at the end of that subroutine, when returning from that subroutine, all of these procedures or steps would need to be performed more or less in reverse order to implement the semantics of the function call return. Another feature that was often added would be some sort of complex addressing mode. So there would be addressing modes that would enable you to provide operands to arithmetic and logical operations directly from memory, perhaps even indexing into arrays or dereferencing pointers, or even using indirect addressing modes where you're actually chasing pointers to pointers that are both stored in memory. The net effect of this kind of complex support embedded directly into these complex instructions was that the data path and the control for the data path that needed to exist to support all of these operations within the context of a single instruction became quite complicated. The real revolution is really started by the 801 project at IBM compiler technology. This eventually evolved into the PowerPC instruction. This is something that you can learn about in contemporaneous with that and Spark projects curious on the West Coast. Maybe some of you have also started that course. And also over in compiler optimization essentially was able to close the semantic gap between all of these processors or primitive designs and instructions using software automation revolved around this notion. The realization that our primitives came to pretty much in line with this technology kinds of available was we saw in the MIPS providing a simpler substrate, of course, a number of variations set of primitives in the machine substrate that really made some of these optimizations and optimizations that wouldn't even be possible if all you had were these complex semantics instructions. So, for example, many times the leaf function in your program, in other words, a function that doesn't call any other function inside it, won't even need a stack frame. It can actually exist without a stack frame, and we can avoid the overhead of allocating a stack frame entirely. It's not possible to do that if your instruction set requires you to allocate a stack frame for every procedure call. But if you have simpler, more streamlined primitives that you use then to assemble a sequence of instructions that implement the semantics needed to support a function call. In the case of a leaf function, you can simply delete out of that sequence of instructions all of the instructions that relate to allocating and deallocating the stack frame. So we can essentially make our code more efficient but only if we provide these simpler primitives. A similar kind of optimization can be performed on redundant loads and stores to and from memory. If, for example, in your program you repeatedly access a particular variable in memory with a complex instruction set, you'll typically actually go to memory for each of those accesses. If you're accessing the variable I over and over and over again in some loop body, for example. With a simpler instruction set that allows you to specify operands from registers, you can simply once load that value into a register, and then every time you need to refer to it, you can simply refer to the register. And you can dramatically reduce the number of memory references that are performed by your program, which leads to both better performance and energy savings. So the end result of this was that as a community, we came to realize that there really was no need for direct ISA support for high-level language semantics. We could instead close the semantic gap with some clever compiler technology instead. When we're evaluating instruction set architecture trade-offs, we need to keep in mind, again, the iron law of processor performance. What we're really trying to minimize here is the product of the three terms that contribute to the iron law: instructions per program, cycles per instruction, and seconds per cycle. And the decisions we make about instruction set changes, additions, deletions, features are going to affect potentially all three of these terms, and we need to be aware of what those changes might be. And the interesting thing is that the relative importance of those changes is going to vary through time as the underlying technology changes. So for example, in the 1970s, memory was very limited, memory was very expensive, and so dense instructions were actually very, very important. You wanted your program binaries to be as small as possible, and that was a big driving factor in providing instructions with very complex semantics, but that still required very few bits to specify them. So a lot of the older complex instruction set computing ISAs, some of them are listed here, were in fact very dense in terms of the program footprint in instruction memory. In the 1980s, the technology changed. SRAM became much cheaper. Even SRAM on chip, on the processor chip itself, became possible in reasonably high quantities, tens of kilobytes. And so the simple ISAs started to make sense, even though RISC instruction sets are typically less dense inherently. Because memory was now cheaper, programs would still fit into those on-chip SRAMs, and so programs would run quite rapidly, quite quickly with high performance out of those on-chip memories, and so code density started to matter less for these kinds of computing systems. One of the key issues that we have to keep in mind also is that to provide high performance, pipelining and ease of pipelining of the instruction execution process that we touched on in the introductory lecture is very important. While it's true that even complex instruction sets can be pipelined effectively, this is something that we study in more detail in ECE 752. A simple regular instruction set, all else being equal, is always going to be significantly easier for the implementer to come up with, or the designer to come up with a high performance implementation. And a final issue that is very, very important and can't be overemphasized is the need for legacy support or binary compatibility. Because the software installed base is so large, changing the instruction set in ways that break the ability to keep executing old programs is something that virtually no one can afford to do. Introducing a wholly new instruction set, especially into an existing market, is virtually impossible. One of the key differentiators between very simple instruction sets like MIPS and other more complex instruction sets is the support for more complex addressing modes. We'll look at a couple of them here that are not found in the MIPS instruction set. The indexed addressing mode essentially lets you read two registers and add them together to generate an address. This requires a little bit more complexity and requires additional instruction encodings in your instruction formats to support, but it's ultimately not too bad if you're dealing with load instructions. Where indexed addressing causes problems is with stores, because now even though you still only have three register operands, all three of them are read and none of them are written. And what this means is that you now have to have the capability in your data path to be able to read the store data as well as the base as well as the index. So you need to be able to read three register values out of your register file in parallel, which adds significant complexity to your implementation. Another addressing mode that is common in other instruction sets is an indirect addressing mode. Here you're essentially going to memory to fetch a pointer and then dereferencing that pointer, all in that same operand fetch as part of that instruction execution. So you're actually performing two sequential memory references in that single instruction, which is going to be rather difficult to pipeline efficiently. Another common feature that's added to addressing modes is auto increment or decrement. To accommodate the operand size, you simply add the operand size to the generated address, or even auto update. This is a feature found in the PowerPC instruction set as well as the PA RISC instruction set that HP used back in the 80s and 90s. This is similar to the register plus displacement addressing mode, but it actually has to, at the end of the memory reference, update the base register using the increment value or the offset value. This slide illustrates the auto update addressing mode where you read a register value, you read an immediate offset, you add those two together, that computes the effective address, you access memory with that, and now you take this effective address and actually update the RS source register with that value as well. This kind of instruction is most useful in loops like this one that are iterating through an array, A in this case with the index variable I. Without this instruction, you would need three instructions in your inner loop, one to do the load, one to do the accumulate operation into the sum variable, and then one to increment the index variable I. With an update instruction instead, you simply do a load update and the accumulate, and you don't have to worry about updating the index variable because that's being done as a side effect of the load update instruction. Now, there's a slight potential for error when you do this, which basically means that before you enter the loop, you have to make sure that you've pre-decremented register 8 so that it doesn't skip over the first entry in the array. This table illustrates some of the history of the x86, or it's sometimes referred to as the IA32 instruction set. It was really initially defined in 1978 with the 8086 processor, and then you see sort of incremental additions and improvements to the instruction set over the years. In 1980, floating point support was added. In 1982, they went to 24-bit addressing. In 1985, they went to actually 32-bit addressing with the 8386. In 1989, there was really just an implementation change where pipelining was added to the implementation to provide higher performance. Similarly, in 92, the Pentium processor went to a dual issue or superscalar design that improved performance again. Similarly, in 1995, Intel came out with the Pentium Pro that supported out-of-order execution. In 1997, the MMX extensions were first introduced. These were the first version of media subword extensions that Intel supported in their designs. This is something that they've continued to evolve. In 1999, they introduced the SSE extensions or streaming SIMD extensions. There have been over the last 15 years, additional revisions of SSE providing additional instructions, additional data types, and higher performance. A big change occurred in the year 2000 when actually AMD, who was designing compatible parts to Intel's parts through much of this history, actually introduced 64-bit extensions to the instruction set. So they extended the address width and the register widths to 64 bits and added all of the corresponding 64-bit operations to the set of ALU instructions as well. The surprising thing about this is that this 64-bit extension came from AMD rather than from Intel, and there's a complicated internal company politics there. Intel basically had a parallel project at this point in time called the Itanium that was focused specifically on support for 64-bit computing, and because of internal politics, they were unable to extend their existing instruction set to 64 bits. And so AMD had an opportunity to get that proposal out the door first. Later on, Intel ended up adopting the AMD extensions into their own product line as well. Most recently, the Haswell line of processors added support for transactional memory, which is an interesting feature that if you take ECE 757, you'll learn about what that means. But it's instruction set mechanisms that provide support for efficient parallel programming in multi-core systems. All right, let's move on and talk a little bit about the Intel 386 instruction set architecture. Let's take a look first at its register model and memory model. In the 32-bit version of this instruction set, there are 8 32-bit registers. However, the ISA also provides backward compatibility to 16 and 8-bit modes with subsets of the 32-bit registers that are accessed by using a different form of the register identifier, EAX for 32 bits, AX for 16, and so on. There are also 4 special registers, including a stack pointer and a frame pointer. The instruction set does include condition codes for overflow, sign, zero, parity, and carry. And the floating point unit uses an 8-element stack. So rather than using explicitly named registers, instead you refer to registers that are in the stack. And the destination register for floating point operations is typically just the top of the stack, implicitly, without having to specify that separately. The memory is a flat 32-bit address space, or there are also some modes for segmenting it that are rarely used, that are more legacy from previous versions of the ISA. The most common address generation mode uses an effective address calculation shown here, which means there's a base register that gets added to an index register that's first multiplied by some scaling factor. So this is convenient, again, for accessing arrays, where the scaling factor would be the size of each element in the array, plus an additional displacement that gets added to it. Most of the arithmetic and logic instructions in the instruction set are 2 register instructions, so rather than having a separate destination and 2 sources, as we saw in the case of MIPS, in the 386 architecture, the first source and the destination are actually the same. So you can have combinations that look like a register-to-register operation, or a register immediate, or a register memory, or memory register, or memory immediate. And some examples are shown here in red. For example, the move instruction, the first one here, will essentially take the immediate value 23 and move it into register EAX. The negate instruction only takes one operand. It actually reads the contents of memory at EAX plus 4, negates them, and stores the negated value back to the same location. Here's an example of a floating point instruction. The FADP instruction is going to access the element at the top of the stack, that's the ST, and also the element that's 7 slots away from the top of the stack. That's what the ST7 refers to, and will store the result back onto the top of the floating point operand stack. Finally, here's an example of a conditional branch. In x86, they're called jumps. So the JLE is a jump if less than or equal to a label. And here the PC will be assigned to the value of the label if the sign or the 0 flag are set. In general, the 386 instruction set is a bit of a decoding nightmare once you start worrying about having to build hardware that reads these encoded instructions in and tries to figure out how to execute them. Because the instructions can vary from 1 to 17 bytes, the decoder actually has to look at all of the 17 bytes to figure out where the instruction actually begins and ends. There are also optional prefixes and postfixes that can be prepended or appended to otherwise valid instruction words that alter their semantics. For example, the 64-bit mode that AMD 64 adds to this instruction set uses a prefix byte that comes ahead of the particular instruction that is to be executed, and the prefix byte specifies that 64-bit semantics need to be applied. There are many crazy formats. The register specifiers move around. They're not nicely aligned like they are in MIPS. But the key core set of 32-bit 386 instructions is really not terrible. It is feasible to implement a pipeline that processes them fairly effectively or efficiently. However, the reality is that if you're going to ship a processor that executes this instruction set, you have to support all of the instructions. And so the hardware still has to deal with all of the complexities, ugly formats, and so on that are included in the ISA. The current approach that Intel and AMD use to tackle this problem is to, rather than executing the instructions themselves directly in the data path of the processor, they have decode logic that takes the complex instructions and translates them to what are called UOPs or micro-ops, which are internal instructions to the machine that look very much like the kinds of instructions that we're used to seeing in instruction sets like the MIPS instruction set. So these are register to register for arithmetic and logic instructions, and load and store with simple addressing modes, like we also saw in MIPS. So the execution core itself will then run these RISC UOPs. This provides backward compatibility and also requires a very complex decoder, because the decoder now has to not just read the original encoded instruction bits and correctly interpret them, but also has to emit a correct stream of UOPs now that implements them. But the main advantage of this approach is that the execution unit is more manageable in terms of its control logic and its data paths, because it only has to deal with these relatively simple primitive units of execution rather than the complex beasts that the instruction set also includes. For the purposes of this course, in particular the project for this course, we use MIPS, or a MIPS-like derivative instruction set, to keep it simple and clean so you can maintain your sanity. If down the road you end up being employed by Intel or AMD, you'll get plenty of chances to learn how to implement x86 processors at that point. Oftentimes, we actually observe some surprising results when we look at these complex instructions. The more powerful instructions are not necessarily any faster than the same underlying algorithm implemented with simpler primitives. For example, string copy is an operation that is frequently used in programs that manipulate strings and deal with textual data. The first option might be to use the move instruction from the x86 ISA with a repeat prefix that allows you to essentially cause the following instruction to be repeated multiple times. As an alternative, you could simply code up a loop that uses loads and stores to and from registers. So these are these generic instructions, as opposed to the very special purpose repeat prefix in front of a move that would not be available in most simpler instruction sets. It might actually be the case that if you coded these both up, the second option could actually be faster on the same machine. But that just reminds us that speed is not necessarily the only constraint, or even the most important constraint. It's pretty obviously going to be clear that the loop that includes the loads and the stores and the branch overhead is going to be larger in terms of its instruction footprint than the first option. So you do get better code density with the first option. And in scenarios or environments where the size of the instruction memory is actually very important, perhaps because there's simply a fixed capacity available, or because of energy constraints, accessing a larger memory is going to consume more energy, that smaller footprint might actually be the better engineering solution for that particular environment. So the bottom line here is it's not always immediately obvious which is better, and you really have to do the careful trade-off analysis each time. Another issue that comes into play as we deal with different instruction sets is the issue of endianness. Endianness describes the byte layout that is used for multi-word data types, or multi-byte data types. So for example, if you have a 4-byte integer that consumes four byte addressable locations in memory, you have to make a decision about what order you're going to store those 4 bytes in. Obviously, you could store them in any order, but what's typically done is what's either called big endian or little endian. And with a big endian approach, the most significant byte is stored at the address where the byte address ends in 00. Conversely, for little endian, the most significant byte is stored at the address that ends in 11. So if you were to lay the addresses from left to right in increasing address order from 00 to 01 to 10 to 11, big endian would have the most significant byte on the left, and little endian would have the most significant byte on the right. And there are examples of both big and little endian instruction set architectures out there. Some even support both, including more recent versions of MIPS than what we look at in this course. The main problem with endianness is that it causes headaches when you're trying to compile code that contains any kind of ugly pointer arithmetic that makes assumptions about how the data is laid out, and also when you're communicating from one machine to another. If the two machines don't agree on endianness, part of the communication protocol, whether it's over Wi-Fi or over Ethernet or over a serial link, would have to take care of reversing the byte order for those multi-byte data types that are transferred across that link. Summarizing this lecture, x86 as an instruction set is definitely not regular. The instructions vary in length. There are prefix and postfix bytes and many other complications. It's not simple. There are many addressing modes that are supported, many instructions with their complex semantics. However, high performance is still possible, requires a great deal of designer cleverness, and the fundamental approach that's used these days is to translate the complex instructions to sequences of simple and easy to pipeline operations. If you're interested in this topic, we spend a lot more time talking about it in ECE 752.